we will try to discuss. That is the forced convection during heat transfer lab. So it's the experiment number 5 in the manual. Everyone can open the manual and check it. The experiment number 5, forced convection. So the aim of the experiment is to determine convective heat transfer coefficient H. So the entire experiment is based on the principle of Newton's law of cooling, which is heat transfer by convection is equal to the convective heat transfer coefficient and the product of surface area, surface temperature and the fluid temperature. The arrangement is being written here. So the arrangement is there is a pipe through which the air is entering. So cold air enters at this point and comes out as hot air. So during the entire length, it takes heat from the pipe surface, and the entire heat transfer is by convection. So in this, since the fluid is entering inside the pipe, it's been called as the internal flow. So in the diagram, we have to use the correlations for internal flow, fluid flowing inside the pipe. So to take the readings, there are 3 thermocouples on the surface. That is T1, T2, T3. Please remember the 3 temperature T1, T2, T3 will be on the surface. The fluid inlet temperature is T4 and the fluid outlet temperature is T5. Right? And the type of fluid is air, it's not water. Right? The heat transfer by convection is happening to the fluid from the surface. Now, to measure how much quantity of air is flowing, we need to have a device that is the orifice meter. Orifice meter is fitted to measure how much quantity of air is flowing. The 2 links of the orifice meter is connected to a manometer. So the value from the manometer gives H1 minus H2. So this value of H1 minus H2 is being used to calculate how much quantity of air flowing. That is mass flow rate of air. Right? Now with this arrangement, we'll go to the equipment to take readings and keep the manual along with you to see the tabular column and which are the readings to be taken and for the further calculations. This is the forced convection equipment available to us. Right? So what is this? Is the pipe. So surrounding that outside it's the thread that's been insulated. Right? So this is the air inlet and this is the air outlet. Right? So I told you the cold air enters. Right? The cold air enters here. It takes heat over the entire length and hot air is coming out. Right? Since it's forced convection, we have to make the air to flow by external means, by a fan or a blower. Right? So here you can see the blower. The blower which blows the air, it passes through this orifice plate. This orifice plate is required to measure how much quantity of air is flowing. Right? Then it passes through the inlet of the pipe. Right? And it goes out to the atmosphere through this pipe. So before conducting the experiment, the observations we have to make a note. Right? First one, the diameter of this pipe. Right? The pipe is this, air is flowing inside the pipe. The diameter of the pipe is there in the manual also, capital D 38 mm. We have to convert this into meter. Next, length of the pipe. Length of the pipe is 500 mm. We have to convert it into meter. Then the diameter of the orifice plate. The diameter of the orifice plate is here, and its diameter, what I am showing now, that diameter through which the air flows is 25 mm, and its coefficient of discharge CD. So these 2 values are required to calculate mass flow rate of air. Right? How much mass flow rate of air going into the pipe. So the procedure of conducting the experiment I am starting now. Right? So there's a main switch, right? And there is a console switch here. Right? This is the blower switch. I repeat, this is the blower switch. This is the heater switch. Right? We are supplying heat to the surface of the pipe. Then there is a voltage and current readings. How much is the voltage and current reading going to the heater? Then the temperature indicator. In this, there are three thermocouples that measures T1, T2, T3 on the surface. And this is the air inlet temperature T4 and this is the air outlet temperature T5. Obviously, after taking the readings, we can check T5 should be greater than T4 because it takes heat, the air takes heat when it passes through the tube, and the heat transfer is by convection. So now we will see taking the readings by starting from switching on the main switch. So the main switch is here. We can switch on the main. After switching on the main, switch on the console switch. Console switch is on. Right? After that, we have to switch on the blower, then switch on the heater. I repeat, don't switch on the heater, then the blower. First switch on the blower, then the heater. We can keep this heat control between 6 to 7. We can keep this knob between 6 and 7. The heat control knob, what I am showing now. Right? Next, switch on the blower, then switch on the heater. After 10 minutes, after reaching steady state, you take the readings. Which are the readings you have to take? I will switch off the blower because of the audio problem. So we have to take the readings after 10 minutes, after reaching the steady state. So the first tab, open the tabular column in the manual. The first column, what we have is the power, that is voltage into current. The first reading, voltage into current. Next, there are 5 columns related to the temperatures, that is T1, T2, T3, T4, T5. That is, there is a knob here. First one is T1, turn the knob, you will get the temperature T2, turn the knob further, it will give T3, T4 and T5. Finally, the next column is the manometer reading, H1 and H2 on the manometer. What I am showing now, H1 and H2 right, on the manometer. This is connected to the orifice blade. Right. May note the value of these two. This much is only the readings to be taken for forced convection. Right. The rest is only the calculations. Right. So after taking all the readings, don't come out of the equipment directly. Right. First switch off the heater. After 2 minutes, switch off the blower. Then go back to the main and switch on the main. This much is the taking the readings of from the equipment. This part that we'll go to the manual and do it. Now we have conducted the experiment, and I am writing the values on the tabular column available in the data handbook. In the manual. Right? So the first reading, voltage into current, it is 179.2. Right? Next, I have noted the 5 temperatures. So the first temperature is 73.7, second is 95, third is 91, T3 is 91.7, fourth temperature is 43.4, right? Fourth temperature is 31.3, then 43.4. Right? Then the manometer reading, which is 2.3 and minus 1.8. Now this much is what we have got the values from the equipment. The remaining is the calculations. Right? Please calculate the H in meter, that will be 4.1 into 10 to the power of minus 2 meter. Right? Now further we have to calculate the equation so that we can get the value of H, convection heat transfer coefficient. So in this you can definitely see the calculations part. The first one, practical approach. Right? First, in that, mass flow rate of air. Right? This equation is related to the orifice meter, what is being used to conduct when you are conducting the experiment. Mass flow rate of air is density of air. We can take it as 1 kg per meter cube. CD of the orifice. Small a is the small area of the orifice opening. Next, root of 2gh rho w by rho a. Right? So substitute the values into this and we get the mass flow rate of air. Right? I repeat with the values here. Rho a is 1 kg per meter cube, CD 0.6, small a is pi by 4 small d square, that is pi by 4 25 mm square, right? Into root of 2 into 9.81. H is the manometer reading in meter. Right? Then rho w 1000 by density 1. Right? So value what we get is in kg per second. mass flow rate of air in kg per second. Next, second one is the how much heat transfer happened. Right? How much heat transfer happened is how much heat taken by the air. Right? So Q is equal to mass flow rate of air into specific heat of air, not water, T5 minus T4. T5 is the air outlet temperature, T4 is the air inlet temperature. Right? Substitute the values. Mass flow rate of air in the previous one, Cp of air 1.005 into 10 to the power of 3 kg per joules per kg Kelvin. T5 is 43.4, T4 is 31.3. Right? By doing this, we can get Q in watts. Right? Third, we have to know the surface area. In the Newton's law of cooling, we need to know the surface area value. Surface area of the tube. How much is the inner surface of the tube? Right? That is pi into capital D into L. Capital D is the diameter of the tube, diameter of the pipe. 38 mm should be converted to meter. The length of the tube, that is 500 mm, it should be converted to meter. Right? Substitute all these, we'll get surface area in meter square. Right? So the last step to find out convection heat transfer coefficient is this Newton's law of cooling. Q is equal to H AS Ts minus T infinity. Right? So in this, the surface area is the average of three temperatures. We already know that T1, T2, T3 is on the surface of the pipe. So Ts or Tf is the average of these three temperatures, right? And the fluid temperature is average of T4 and T5, right? That is air inlet and air outlet temperature. Substitute all these into the equation, we get H practical. So the unit of H practical I am writing, H practical unit is watt per meter square Kelvin. Right? This is the convection heat transfer coefficient by conducting the experiment. Whatever the value we got is this. Right? Next, right? So we can also find the convection heat transfer coefficient by theoretical approach. For that, we need to frequently use the data handbook. Right? So first one, bulk mean temperature. At what temperature we have to take the properties of air, not water. Fluid is air. So fluid air temperature is Tm. Right? At this temperature, T4 plus T5 divided by 2. At this temperature, we have to find the properties of air like density, viscosity, Prandtl number and thermal conductivity. We have to note down the following properties from data handbook. Now what we are seeing is a theoretical approach to calculate the convection heat transfer coefficient in forced convection. Right? So to find out in the theoretical approach, the first thing is we have to find out the properties of air. The fluid is air, so not water. Right? So we have to find out the properties of air at a particular temperature. That temperature is called the bulk mean temperature. This bulk mean temperature is the average of air inlet and air outlet, T4 and T5. Right? So we will get a value based on the readings whatever we got. Right? So with this reading, right, we have to use the data handbook. Right? So frequently we have to use the data handbook for this theoretical approach. Everyone, please open the data handbook. In the data handbook, page number 34, what we can see now, right now on the video. Right? Page number 34, property values of gases at 1 atmospheric pressure. Right? And we are taking the properties for dry air. Right? So next page we have nitrogen, oxygen. Right? So dry air we have to take the values. Right? For dry air at this temperature, right? Suppose if we get the temperature as 40 degrees centigrade. Suppose if we get temperature as 40 degrees centigrade, note down these property values. Which are the property values? Density, absolute viscosity, kinematic viscosity, thermal diffusivity, Prandtl number, specific heat and thermal conductivity. You have to just make a note of these values. What I am writing now at 40 degrees centigrade, for example, density 1.128, then absolute viscosity, kinematic viscosity. Like this, you make a note of all the property values. Then coming back to the manual. We have to find out the velocity of air at which it is coming in. Right? The velocity of air at which it is being coming in. Right? So the velocity of air is given by mass flow rate of air divided by density of air into area, capital area. Capital area is not the area of the orifice, it is the area of the pipe. That is pi by 4 capital D square. Substitute all the values into this equation, we'll get the velocity of air, We'll go to the next page, page number 16. Page number 16. After finding the velocity of air, we have to check whether the flow inside the pipe is laminar or turbulent. To check whether laminar or turbulent, we need this parameter called Reynolds number. Reynolds number is a dimensionless number. It's given by Re is UMD by kinematic viscosity. UM is the velocity of the fluid, that is in the previous page. Diameter is capital D, that is 38 mm. Next, kinematic viscosity of air from the properties of the table of the data handbook. Right? So using this Reynolds number value, we have to use the suitable Nusselt's number equation available in the data handbook. Right? So we will go to the data handbook and open the page number. Right? Open the page number 124. Page number 124, the internal flow. Right? In that we have tubes laminar. Next page we have tubes for which is turbulent. Right? If Reynolds number is less than 2300, we can use these correlations. Right? If Reynolds number is greater than 2300, we can use this. Right? So from our previous experiments, we have got Reynolds number greater than 2300. Right? Hence, it is turbulent. We have to use the correlation of turbulent flow. So please open page number 126. You can see the video now. Right? So in this equation 2.3.1, fully developed flow. Right? We will use this correlation to find Nusselt's number. So I am reading this equation. Nusselt's number is 0.023 RED to the power of 0.8 PR to the power of N. Right? So in this RED is whatever value we got. Right? And Prandtl's number is the property value we have got from the data handbook for air. Right? So in this equation you can definitely check small n is equal to 0.4 for heating of fluids, small n is equal to 0.3 for cooling of fluids. In the experiment whatever we have done, air is heated. Right? So it is heating of fluids. So we have to substitute small n is equal to 0.4. Right? So substituting all these values, we get a Nusselt's number value. Right? Using this Nusselt's number value, the last equation to calculate the H is this. Right? H is Nusselt's number into thermal conductivity of air divided by diameter of the pipe. Right? Thermal conductivity of the air we have got from the property table. Right? Diameter, right, is we got the Nusselt's number from this equation. Now the last step to find out the convection heat transfer coefficient by theoretical approach. That is H theoretical is NuK by D. Right? So K is the thermal conductivity of air and D is the diameter of the pipe, that is 38 mm. So substituting this value we get the H theoretical. So where we got this formula is not from directly from the sky. It's available in the page number 112 in the data handbook. So you can see now the data handbook page number 112. In that we have all the equations. In that Nusselt's number we have HD by K. So from this page we got the we can definitely use this formula. Right? So after finding H theoretical, we have to compare the convection heat transfer coefficient by practical approach and also convection heat transfer coefficient by theoretical approach. Right? So we can write the result. The convective heat transfer coefficient in forced convection is dash watt per meter square Kelvin by practical approach, that is previous one. Right? And theoretically, by using the correlations for these conditions, convective heat transfer coefficient is dash, that is this value whatever we got recently. Right? So these two values will not be same because there is a losses happening by in the pipe. The convection happening is not proper and the flow will not be always steady state, and there is fluid properties getting continuously changed, right? And there is frictional head loss. All this accumulates to the difference between H practical and H theoretical. So that is the aim of the experiment what we had to find out the convection heat transfer coefficient in forced convection. Please remember the unit watt per meter square Kelvin. Right? So this much is the forced convection heat transfer that's been available in the page number 13 in the manual. Right? So thank you very much guys, all the best.